Flip Tarver for Precalculus. In this video we're going to be taking a look at partial fraction and partial fraction decompositions. Our objectives for this lesson: by the end of this lesson you'll need to be able to write a rational expression as a sum of partial fractions, and you need to be able to write an improper rational expression as a sum with partial fractions. Our outline for this video will kind of take a look back at, where does this whole idea come from by taking a look at how we add two rational expressions. Then we'll take a look at a process behind solving partial fractions and finding what we refer to as partial fraction decompositions. Then we'll take a look at what we have to do when it's an improper rational expression. And then finally we'll be taking a look at kind of a special case where that bottom of the rational expression is a little bit more complicated. So let's get started. Just if I asked you to add these two rational expressions, two pretty small, simple rational expressions, if we wanted to add these, you know that we would need a common denominator. And our common denominator when we do this is to take our two denominators and multiply them together. So, one way I like to explain this is our common denominator is x minus 5 times x plus 4, and each of those fractions is missing one piece or the other, so I have to give them the piece that they're missing by multiplying on the top and on the bottom. So the first fraction is missing the x plus 4, so I multiply that in on the top and on the bottom. Remember, when we're multiplying by x plus 4 over x plus 4, we're really just multiplying by 1, which doesn't change the fraction. The second fraction is missing the x minus 5, so I multiply that fraction by x minus 5 on the top and on the bottom. So when we do that, we distribute the 2 in. We really don't have to distribute the 1 in, but we distribute the 2 in, and I didn't really bother multiplying it out because I've said before, it's actually really nice when these things are factored out. You're going to find out that, if they're not factored out, you've got to factor it out. So a lot of times I don't multiply the x minus 5 and the x plus 4. A lot of times I don't multiply the bottom. But we would combine like terms on the top. And if we did multiply the bottom together, it's just a quadratic. So what we're really going to be learning today is how to do the exact opposite of this, which isn't quite as easy as it sounds. But that's really what partial fractions is all about, is taking these rational expressions that are products on the bottom and saying, it would be easier if instead of one big fraction, it would be easier if I could split these up and write it as a sum of smaller fractions. So let's take a look at an example where we have a nice little quadratic on the bottom, x squared minus x minus 2. We're going to be factoring that out. And, we've got a pretty simple top, a pretty simple numerator to this rational expression. This is proper, quote unquote proper. I hate that term. But, it is proper because the power on the top is smaller than the power on the bottom. We will be looking at an improper case later in the video, as you know. So our first step is to factor the bottom. So it's a nice basic quadratic, isn't too difficult. Factors into x plus 1 times x minus 2, and you should be able to do that. And now what we want to do is break this up into a fraction that is over top of that x plus 1 plus a fraction that's over x minus 2. So what we've got to figure out is what's the top for those two fractions. So what we like to do is write them as the two fractions with a on top of 1 plus, and then the other fraction with b on top of 1. And what we've got to do is figure out what the a and the b are. Now these are going to be numbers. A and b are just going to be numbers, because if it was something more complicated than that, we'd probably be breaking it down even further. So we got to figure out what a and b are. How do we do this? Well, our first step, I've actually got two methods to show you in this video. A really simple one, and then a nice workaround when things start to get complicated. The first thing that we're going to do is, whenever we want to solve equations like this, well, these are fractions. We've got these denominators in here. It'd be nice if these denominators went away. So you multiply the whole side, the whole equation, both sides, by the x plus 1 and multiply it by the x minus 2. when you do that, that's going to get rid of both of the x plus 1s and the x minus 2 on the left side, and it's going to get rid of the x plus 1 that's under the a. It's going to get rid of the x minus 2 that's under the b, but it's going to introduce some things on that right side. So let's go ahead and multiply this whole equation by x plus 1 and multiply this whole equation by x minus 2. And because the a was over the x plus 1, that canceled out, but the x minus 2 did not cancel out for that first fraction. And because the b was over the x minus 2, that canceled out when it multiplied, but the x plus 1 did not get canceled out. So now the b is multiplied by that x plus 1. My first method, and again, I said I'm going to show you a great way to do this when things get a little more complicated. But the first method, I'm going to go ahead and distribute the a and the b in. Now you may end up preferring the second method, honestly, but I'm going to show you both, and you got to wait for the second method. So I'm going to distribute the a and the b in, and now I'm going to group these because I've got this ax, that's an x term. I've got this bx there in the middle, kind of. That's an x term. So I want to group these based on whether they've got an x or not. And I even went so far as to factor that x out. Now, if you compare what's on the right side, the a plus b is multiplying the x, compare that with what's on the left side. Well, on the left side it's only 2x. Well, that kind of means that this a plus b has to be equal to 2. Okay, so that lets us write an equation for a and b. And this minus 2a plus b, well, that has to be the constant at the end. That has to equal this 5. So that lets me write two equations that I can then solve for a and b. So I kind of put my original thing, what we're trying to work for, over here up in the corner, just kind of remember where we're coming from. So if you're kind of confused why that's there up in the upper left-hand corner, that's just a reminder about where we came from while we're working on this. So we're going to set the a plus b equal to the 2. We're going to set all the stuff at the end, the minus. Don't forget that minus. That goes with that 2a. So negative 2a plus b, that's got to equal our constant at the end. Well, gosh, how many different ways do we have for solving this system of equations now? Maybe you want to write a matrix equation. Maybe you want to do Cramer's rule. Maybe you just want to do old school elimination, or, Shutter. Maybe you want to do row operations. But what we've got to do is solve for a and b. And I went ahead and I wrote a matrix equation. And I've got to use the inverse to solve that. You should know how to do that. I'm not going to spend too much time talking about this. But solving this matrix equation, I get a equals negative 1 and b equals 3. So remember, those go on the tops of these fractions. That's why I wrote this up here in the upper right-hand corner to kind of remind us what a and b were. So we can now put that negative 1 on top of the fraction. We can put that 3 on top of the fraction. And bada boom, bada bing, we have just decomposed, we have just broken up this product fraction into a sum. And when you hear the term partial fraction decomposition, that's the big fancy term for this stuff over on the right hand side. A partial fraction decomposition, that's what we end up with. That's not the process. That's what we end up with at the end after we've done all of this. So, hey, great job. Really proud of myself. So let's try to make things a little bit harder. Let's look at some improper rational expressions. Now, they're improper because the top power is not less than the bottom power. Even this first one on the left, the 3x squared plus 12x plus 4 over x squared plus 2x, that kind of falls into the improper area because the powers match. Now the one on the right, the x to the 4th power, that's definitely bigger than the x squared. So this is definitely improper. Well, we're not going to do our decomposing right now. We're not going to find our partial fractions yet. What we've got to actually do is divide. I mean, remember, this fraction means to divide. So I've actually got to divide these out. Now, you might, go running and screaming into the night, but what I'm talking about doing here is the long division. We can't use synthetic division because we're not dividing by an easy enough thing. But we've got to actually do this division. It can be a little bit time consuming. Here's my two answers, maybe it sends you screaming into the night, but the first thing I do is I find out what these fractions equal. This one on the left, what I've got is a whole number, so I can say that it's equal to 3, and then this stuff right here is a remainder. So what I really need to do with this remainder is put it over the original denominator. So this first fraction is equal to 3 plus 6x plus 4 over x squared plus 2x. So that's now a proper fraction, and that proper fraction at the end, that's what I have to decompose. I don't have to decompose the 3. Looking at the one over on the right, we see x squared plus x plus 5 on the top, and then down here on the bottom, this is the remainder. So this big nasty fraction on the right is equal to x squared plus x plus 5 plus 11x plus 4 all over the x squared minus 4x. So it's that fraction at the end that we have to decompose. We don't decompose the x squared, the x, and the 5. So let's go ahead and we're going to go ahead and focus on one of these, and we're going to decompose one of these, and well, we're going to decompose the bigger one. Okay, so really, again, what we're decomposing is this remainder fraction at the end. That's what we're focusing our energy on now. The x squared, the plus x, the plus 5, that's done. We're not decomposing that. That doesn't need it. So we're going to focus on that fraction at the end. We can factor out an x, and we've got x times x minus 4. That's what we're going to break it up into a fraction over x plus a fraction over x minus 4. So we're going to do all this process that we just learned or just saw me do on the remainder fraction. So let's go through this process. We're going to multiply by x. That gets rid of the x on the bottom. On the left, that gets rid of the x under the a. There's no x under the b, so the b ends up with that x. We're going to multiply by x minus 4. That gets rid of the x minus 4 on the left. That gets rid of the x minus 4 under the b, but there isn't one under the a, so the a ends up being multiplied by that x minus 4. Go ahead and multiply or distribute our a, just like we did before. And I'll group the a and the b, x, together. And we'll go through the same process here where the a plus b has to be equal to that 11 in front of the x on the other side. The minus 4a, well, that's got to equal our 4. Wait a minute, that looks really easy. And sometimes that works out like that. I mean, we don't have to do fancy stuff here. You can spot that right away, that a has to equal a negative 1. If it falls apart like that so easily, go ahead and do that. So my a is equal to negative 1. I plug that into my top equation, solve for my b, and b equals 12. So, sometimes the answers just kind of fall in our lap, and that's great when that happens, but sometimes we got to work a little harder. Now, that is not the second method that I've alluded to a couple times. That's still coming up. That was just, an example of where our answer was pretty easy. So we're going to put the negative 1 over the x. We're going to put the 12 over the x minus 4. And don't forget where this came from. We're trying to decompose this big, nasty-looking improper fraction. So we've got to include the x squared, the plus x, the plus 5 that was there after our long division. So don't forget about that stuff. Don't forget where the problem came from. And here is my final answer, that this big, nasty, improper fraction equals x squared plus x plus 5 minus, because a was negative 1, minus 1 over x plus 12 over x minus 4. Okay, so let's take a look at a kind of a special case. Now, this fraction in and of itself is not the special case, but it's an example of this special case where we have factors occurring more than once. Now, what do I mean by that? Well, okay, first of all, let's take a look. It is a proper fraction. We have a lower power on the top than we have on the bottom. But you might be looking at it going, Mr. Harber, that's not a quadratic. No, it's not. So we're going to have to work just a smidge harder to factor this out. And what we get is a bottom that factors into x times x minus 1 squared. Now that's the special case. The fact that this is squared right here, this is really what I'm talking about. And you'll see I have three fractions. Why is there three fractions? Because I'm basically allowing for the possibility that this didn't just come as one fraction over x and one fraction over x minus 1 squared, but I'm allowing for this repeated factor, this square, to have occurred as x minus 1 in one fraction and x minus 1 squared in another fraction. And I basically, you could think of it this way. I have to keep on adding fractions until I build up to the power that I have. So the x minus 1 is squared. I have to have a fraction that accounts for x minus 1, and then I have to have a fraction that accounts for x minus 1 squared. If, shudder, gasp, if the x minus 1 was cubed, I would actually have an x minus 1 fraction. I would have an x minus 1 squared fraction, and I would have yet another fraction for the x minus 1 cubed. Now, the possibility is that x minus 1 fraction was never there. And in that case, what I would find out is that b is 0. And that's okay. If you end up in a situation like this where one of your fractions ends up being 0 on top, that's okay. That just means that that fraction isn't part of the solution. Still going to go about this the same way. I'm still going to multiply by my big denominator. I'm going to multiply by the x. I'm going to multiply by the x minus 1 squared. That gets rid of them totally on the left side. The a gets an x minus 1 squared. It doesn't have the x anymore. The b, this is kind of the problem child. B gets the x, and it gets one of the x minus 1s because it only had x minus 1. So when I multiply by x minus 1 squared, it's stuck with one of them. And then the c has enough x minus 1s. It had x minus 1 squared under it. So it canceled all those out, but it still got the x. Now, you might be going, Mr. Harbert, I've got x squareds on the right. I've got no x squareds on the left. Does that mean I've got a problem? No, that does not mean we've got a problem, but that does mean I'm going to switch to this other method that I was talking about. And what that means is I'm going to plug some numbers in for x, but I'm not just going to do this willy-nilly. I'm going to be really smart. I'm a smart guy. So if I get to plug numbers in for x, I'm going to plug in numbers that are convenient to me. Let me show you what I mean by that. So I get to choose whatever I'm going to plug in for x. Yeah, I could just sit there and go, you know what, I'm going to plug in 5, I'm going to plug in 10, I'm going to plug in 32, all my favorite numbers, all the numbers that, won in the last lottery or something. Okay, don't do that. Pick numbers that are going to make terms go away. Pick numbers that are going to make zeros for you. So here's a real obvious one to pick. 0. Look at the second and third terms on the right hand side. When I plug 0 in for that x, it gets rid of my b term and it gets rid of my c term. Those are gone. When I plug in 0 in the a term, okay, that a term is still there, but you know what I get to do now? I get to solve for that a with no b and no c in the way. Make sure you plug in the same number everywhere. Please be very careful when you're doing this. Don't rush through it. That 0 minus 1, that's negative 1, I square it, turns into a positive 1. So things are just working out beautifully when I plug in 0. So that lets me say that a equals 2. Whoa! I didn't even need to set up a matrix equation. I've already got a. Okay, so what would make sense? What would make, let me see. I got to pick something to plug in that's going to give me zeros. How about negative 1? Excuse me, how about 1? Because that x minus 1 is going to go to 0 now. So this is going to make my a go away. This is going to make my b go away. And I'm going to be able to solve for c. So when I do that, c is equal to 3. Oh my God. I've got 2 of my 3 letters. All right. Can I think of something else? I've already used 1 to get rid of the a. Okay, well, I'm kind of out of numbers that are going to make terms go away, but I already know what A is, I already know what C is. So just pick another nice number, plug it in, plug in what your A is, plug in what your C is, and you will be able to solve for B. So I decided to plug in 2. Plug in 2 all the way around, okay? Go ahead and plug in 2 for your A value and 3 for your C value. And now you can solve for your B. So this method is probably going to be the one that you do the most, okay? Why do I save it for the end? Yeah, you know, you got to save the good stuff for the last or else you guys won't watch the whole video. So choose your X values so that it makes terms go away. And in this case, I got B equals -2. So now remember, I'm not asking what is A, what is B, what is C. Remember, I'm creating a partial fraction decomposition. So, you know, I've got to plug in what my number is for A, what my number is for B, what my number is for C. And that is going to give me my answer. So here is my partial fraction decomposition for this fraction with repeated factors on the bottom. All right, looks like it's time for you to get to work. I'll see you in class, and I will see you online.